So now we're going to talk about the periodic trends found on the periodic table. They'll be discussed in no particular order, but just so we're on the same page, periodic trends refer to those characteristic properties that are found in various elements when you look at the periodic table. Now, there are going to be a series of them, and even though they may not hold true in every case, they will show a tendency towards behaving in a certain manner as we discuss them. And we'll also discuss the reasons for these trends. So the first one is perhaps the most important one, and that's the atomic radius. Now, the radius of an atom is not generally measured from the edge to the center because the edge represents kind of an electron cloud, and that can actually be kind of gray and blurry, and it's hard to distinguish. And so as an alternative approach, a lot of times what scientists use is they study the covalent radius. And you determine the covalent radius by essentially attaching two atoms that are bonded together, and you look at the distance from the center of one of those atoms to the center of the adjacent atom, and you divide that by 2. And that will give you a measure of the respective atomic radius. Now, this length is generally measured using angstroms. However, there are some measurements that are represented using picometers. Now, an angstrom is roughly 1 times 10 to the negative 10 meters. Going forward, let's look at an example. Here we have 2 bromine atoms that are shown bonded together. Now, their measurement from the center of one nuclei to the center of an adjacent nuclei represents 2.86 angstroms apart. But again, because we're looking at the actual radius, dividing 2.86 gives us a value of 1.43 angstroms. And so that's how scientists are able to quantify the radius of an atom. Now, the trend for the atomic radius, particularly in the vertical column, is that it goes from smaller at the top to much larger at the bottom. So basically, the atom gets larger as it increases going down a vertical section. Now, why is this the case? Well, as you go down each step within a family or group on the periodic table, you're adding a new PEL to the electron cloud. This makes the atom larger at each step. Now, going across a periodic table, when you move laterally, the trend becomes a little bit less obvious, but it still holds true and will justify why it behaves that way momentarily. Now, when we're looking at the direction from left to right of a period series, the atomic radius tends to actually decrease. What happens is at each step, a proton and an electron, and possibly even 1 or 2 neutrons, are added. Now, the electrons are added to existing PELs, or sublevels, if you will. And what happens is, as you increase in the number of electrons, along with an increase in protons, you increase the effective nuclear charge between the two. This creates a greater pull between the electron cloud and the nucleus of the atom. The nucleus becomes more positive, the electron cloud is more negative. And so this increased attraction is what's responsible for reducing the size of those atoms and makes them smaller going across a period from left to right. Now, I mentioned effective nuclear charge earlier, and that references the attractive force that compels both protons and electrons towards one another. Protons are positive, electrons are negative, and as they say opposites to attract, it holds true when you're referencing the atoms, and thus you have this effective nuclear charge, which represents this pull that exists between the electron and nucleus of an atom. Now, the closer an electron is to the nucleus, the more pull it actually feels. And the further away, the harder it is to keep them intact. Now, as effective nuclear charge increases, the electron cloud is going to be pulled in tighter, which justifies why, as you move across a period on the periodic table, it becomes tighter. Now, the overall trend is going to look more like this depiction here, where you have an increase in the atomic radius going down, and you're going to see a representative decrease going laterally from left to right. Now, if you look at the actual concrete numbers of atomic radii for atoms and elements alike, you'll see that there may be some notable exceptions, but we're looking at it just as a trend process so that we understand the tendencies of the atoms themselves. Now, if I was to write it out and kind of represent that trend myself, I'd probably show arrows showing which direction the arrows would go to represent an increase in this number. And so if you look at my blue arrow here and my blue arrow there, both of those are pointing in the direction that represent atomic radii increasing for atoms. Now we're going to talk about this term shielding. And basically, as more PELs are added to atoms, the inner layers of electrons shield the outer electrons from the nucleus. So basically, with the increase in size of an element, if it moves from an element that features 10 electrons and you jump to compare it to an electron that features 30 electrons, you'll get more shielding because there are more layers to protect between the pull of the outermost electron on an atom and the actual protons found in the nucleus of an atom. Now, the effective nuclear charge on those outer electrons becomes less, and so the outer electrons are held less tightly. Now, we're going to now look at the trend of ionization energy, and it's perhaps the second most important periodic trend, and we're going to not only discuss the ionization energy, but we're going to talk about why it behaves in the manner that it does. Now, if an electron is given enough energy in the form of something like a photon to overcome that effective nuclear charge that I discussed, it can leave the atom. The electrons become able to move on. Now, when this happens, the atom becomes ionized or charged. Now, the number of protons and electrons no longer become equal when this process happens because you've effectively removed an electron. Now, the energy that's actually required to remove that electron represents the ionization energy. And so if you know the tendency of elements to form anions or cations, you would have a general idea of their behavior as it relates to ionization energy. Meaning that the easier that something is willing to remove an electron, the lower the ionization energy. The harder it is to remove an electron, the greater the ionization energy. So also, the larger the atom is, the easier it is to remove that electron. Now, you need to understand that the relationship between atomic radius and ionization energy are inversely proportional. This means that as one increases, the other decreases, and vice versa. Now, also, ionization energy is always going to be endothermic. That it is energy that is added to the atom to remove the electron, not energy that's released. Now, the depiction in the image provided actually shows how this relationship is made possible. Here you see how basically the ionization energy more or less increases as you move from left to right, and it also decreases as you go down the vertical sections. Now, like I mentioned with atomic radii, you'll notice that if you looked at concrete values of this, you'll see that there are going to be some clever exceptions, but we're looking at it as a general trend and not an exact replica of how it should behave based on this exacting trend. So, ionization energy potential, the arrows would probably look more like this, where, as I mentioned, is inversely proportional to atomic radius, which means that the arrows are going to go in a different direction to show as the ionization energy potential increases. So the reason the ones on this side of the periodic table are lower in ionization energy is because they readily give up electrons, while these on this side are way less inclined to give up any form of electrons. Therefore, it will require a great amount of energy to even give up an electron and take another amount, and therefore have a value that's very high for ionization energy. Next, we're going to look at this word electron affinity. Now, when you think of the word affinity, You think of like a fondness or an attraction or something of that nature. Now, when it comes down to electron affinity, it is the energy change that occurs when the atom gains an electron. This is measured in kilojoules as well. Now, where ionization energy is always endothermic, the electron affinity is usually exothermic, but not always. And so this is what happens to this is following the addition of an atom. And so that's what that quantifies. Now, electron affinity is exothermic if there is an empty or partially empty orbital for an electron to occupy. So if it has a blank space and it receives that electron, the energy change is going to be an exothermic reaction. Now, if there are no empty spaces, a new orbital, or PEL, must be created, making the process endothermic. So what we should get from that is that in some cases there's an exothermic occurrence, and in some cases there's an endothermic case. I will say this, it is my understanding that the exothermic is preferential because it fills those orbitals, and it's easier to fill them than start a new PEL. Now, this is true for alkaline earth metals and the noble gases, where they tend to not be willing to receive electrons as willingly as some of the other main group elements. So if you were making a help sheet, your help sheet would look kind of like this, where to show the value of where it increases, it goes up as it's going from bottom to top, and it increases going from left to right in terms of electron affinity. Now, the marks here also denote that you kind of can ignore the values here for those columns because they're not going to have a value that really can be compared. Now, metallic character is a little bit different. This is a simple relative measure of how easily atoms lose or give up electrons. Your help sheet for something like this should look like this. Obviously, if you have a general understanding of the periodic table, most of the metals are going to be found, if not all of them, going to be found on your left side of your periodic table. Knowing this, you're going to use that to navigate and understand that metallic character increases as you go from right to left. It increases as you go from top to bottom. Electronegativity is a measure of an atom's attraction for another atom's electrons. That's the tendency of an atom to desire electrons, and they assign values falling between 0 and 4 according to a Pauling scale. So the units of electronegativity is called Paulings. It may not be super vital, but it's important to note that the electronegativity values are rated from 0 to 4, 4 being the highest, which we'll find out that that is fluorine. So generally metals are electron givers and have low electronegativities. Nonmetals are electron takers and have higher electronegativities. Recall that this deals with the atom's attraction for another atom's electrons, so it kind of makes sense if you understand your main group elements, because generally main group elements want to have those electrons to themselves, the ones on the right side. Now, as far as noble gases, they're not going to really contribute to this because they don't have an attraction for another atom's electrons because they have reached octet. They are content. Now, if I was writing a help sheet, mine would look like this, where I'd have my arrows showing that it increases going from bottom to top, showing that the values increase going from left to right. Fluorine is going to be somewhere right here. Your noble gases are not going to have an electronegativity value because they don't need electrons. They're not attracted to electrons. They're generally stable and therefore do not generally seek out other electrons. Now, overall reactivity is a little bit of a mixed bag. It tends to tie all the previous trends together in one little package. However, you must treat metals and nonmetals a little separately. Now, it's understood that the most reactive metals are the largest, and they're generally the best electron givers. And the most reactive nonmetals are the smallest ones, which are the best electron takers. And so if we were drawing our diagram help sheet to look and describe it, it would be a combination where you'd show arrows going this way for your metals that show the greatest overall reactivity, and you show the arrows here to represent the non-metals that show the least amount of reactivity. And again, noble gases do their own thing, so they're negligible. They have a value of 0. You don't use them as a form of comparison. If you were, they would always be the lower end. Now, the octet rule represents this goal of all elements to achieve 8 valence electrons. That's 8 electrons in its outermost shell in its valence energy level, and that applies exclusively to the main group elements. And you'll look at those tendencies and behaviors because they will dictate what an atom wants to do, whether it wants to give up electrons or accept electrons. And basically, from a general standpoint, metals generally give up the electrons, and the nonmetals take them from other atoms. And that's how their behavior is. Now, when this process occurs, an atom goes from being neutral to becoming something called an ion, which represents a charged atom. Now, it will either gain or lose an electron to become this, but it is an ion. Now, when an atom gains an electron, it becomes negatively charged. This is called an anion. Once again, it is gaining an electron. So if I'm looking at this gaining of electron where basically an atom is reduced, it becomes an anion, which is negatively charged. In the same way that non-metal atoms can gain electrons, metal atoms can lose electrons. And so these are called cations, and those are going to be the ones that generally go through some type of oxidation process to form these cations. Now, here's a simple way to help you remember. It's a little bit cheeky, if you will, but it helps with mastery of understanding the dynamic difference between cations and anions. The image shows Anne, a negative girl who is and the ion. She's unhappy and she's negative. In the next image, we have Plussy the cat. Plussy the cat is a cat ion. He's Plussy. So cations being positive, anions being negative. Atomic radius. When we're looking at ions, they actually show a different behavior from their neutral counterparts. So cations are always smaller than their original atoms, and you have to understand that the entire outer PEL is removed during ionization. Conversely, if you look at anions, they are always larger than their original atom, and this is because they gain a greater amount of electrons, and they kind of float there. So that's kind of what we're getting at with that. So let's look at this just brief description of how a cation forms. Generally, before an ion forms, you have 2 neutral species where it has the same number of electrons, same number of protons, and when it goes through a process of basically losing an electron, it now becomes kind of a dynamic difference between the number of electrons and the number of protons. Conversely, you end up having, conclusively, you end up with more protons and more electrons, more positive, and this is your cation. Now, because of that, this means that the central pull of the proton is greater, and it pulls it tighter because of the effective nuclear charge. So here's how that shows that image. Now, I want to go ahead and take this chance and look at the anion next, and that one's going to be dynamically different. Basically, when you have anion formation, you have it gain an electron, and when it gains that electron, the effective nuclear charge is pull is affected because you have more electrons now versus the number of protons, and because there's not enough protons to create that effective nuclear charge, it results in changing the distribution. Therefore, the anion ends up being larger than its neutral counterpart. So in this case, we'd be looking at something like chloride. And that completes today's lecture on periodic trends.